So I want to show you all something today with the Tesla turbine that I came up with a very long time ago. Around 2019 I had at least drawn this, but I figured this out a lot earlier. So I had been working on the turbines. This was one of the very first ones I had. Maybe you can see through it. Yeah, you can see through it there. This was supposed to be a two-stage, kind of like this, but it was just missing the center. So it went into these small ones right here, and then there's holes inside of here. You can't see that transition between the two stages. Well, the point of all this was, one of the original design features that I had put into this system was that I had come up with a thermoelectric disc stack, where each of the discs of the turbine was made of a different type metal. If you look here, I'll point up a thermoelectric. You use two dissimilar metals and you have a connecting tips, and then you have them connecting at the bottom. And what this would require is alternating conductive and non-conductive star washers that provide the every other connection. And then up at the top here, we do alternating conductive, non-conductive spacers. I have mica spacers and I had copper spacers to do inside of here. Ignore the blood on my hand. These discs get sharp. So what this point of this was when you have a Tesla turbine, the fluid does expand first in the nozzle, but then it still has a chance to expand through the spiral pathway going through the turbine. If that motive fluid is expanding going through the turbine, that means it will be cooler by the time it gets to the exhaust in the center. What that means is there will be a temperature thermal gradient from the tips of the discs to the center of the discs. As such, with this thermoelectric disc stack, with the proper alternating star washers that are conductive and non-conductive, and alternating tip conductive and non-conductive spacers, this creates a thermoelectric circuit that the radial temperature gradient across the disc stack from the tips to the center generates a DC current flow through the axial direction of the disc stack that snakes up and down. What happens here is you take this current and you discharge it so that this tube is separate from the center shaft, so that the positive goes to this center shaft all the way to the outside set of plates, and then the negative goes around the tube on the outside and goes to this set of plates. So there will be whatever the potential gradient of voltage across the disc stack here generated from the radial fluid temperature gradient will produce a voltage potential across the second stage disc stack, which is then used for electrolysis of any remaining fluid. We're already going to have this natural thermal gradient, so by utilizing this to make electricity with it, it actually turns part of the turbine into a solid state electric generator. Why that's cool is that means inside of like a plane or a turbine or a turbojet engine, before the turbine's even spinning up, you could use the disc stack as an electric generator to power onboard electronics or whatever you want inside the thing without having to actually have the turbine even spinning. That's the whole point, was that it has two ways of making power. Once with a rotational mechanical power, and twice with the thermoelectric effect across the disc stack. Corollary, then using that disc stack in a many disc stack electrolysis device, you then get a thermoelectric hydrolysis Tesla turbine that uses the thermal gradient from the radial tips to the center to produce a DC voltage potential. And now the math I had done was I needed about 5-inch discs and about 100 of them. Basic calculations, experiments that I found online, been able to produce X amount of voltage with a single strip of metal that was about the same length. And I did the calculations. About 100 discs with an 80 degrees Celsius temperature gradient should produce about a half a kilowatt and be able to attain at least a 1 to 3 voltage potential. And if you know electrolysis, you need about at least 1.4 volts. So this disc stack should be able to generate at least exactly enough voltage to start electrolysis of any sort of condensate that's flowing in the exhaust of the gas turbine, and or if this is a steam turbine and this condenses anywhere. If you check out my other video up here, I have what's called as the interstage heat exchanger. Makes this tubes here be a bunch of extra discs that go up much further here that allow for external air to come through, go through the extra outside discs, and that cooling, the air coming through, provides cooling. It cools the flow of the fluid that's going through the center here, and the natural rotation of the turbine allows for it, like the discs that are out here provide the heat exchange area and provide the way of wicking or provide the way of pulling the air and pushing it through, because the disc stack on the outside here works like a blower or a compressor. So the whole rotary system spinning, hot fluids expanding through here, going through here and out to here. This would be isolated from here. You can see this for better in my video, but having this interstage heat exchanger, we can remove heat from anything that's in here. And of course we can continue to do that thermal gradient radius thermoelectric stack of all the discs across, so that this temperature gradient here further adds to the power output here, or the voltage out here. But if you cause some of the steam coming through here, I think the test I had looked at was an 80-degree gradient from 200 to 120 degrees Celsius. And as such, if you can cause any of that steam inside here to condense via the interstage heat exchanger, which preheats combustion air with the heat wicking off the air it's being flung through it with the rotors, that then this moisture that's condensed in here goes into the electrolysis disc stack for electrolysis to be burnt in a second stage turbine. And then this disc stack here also works as a second stage high vacuum pump on the exhaust of this. And then this can be doubled up. You can make it dual-sided so that from there you have positive on this side and negative on this side. So you can collect only hydrogen on this side and only oxygen on this side. As well, it also works as the compressor for it because it's a disc stack compressor. Separate, so you don't have to worry about any sort of combustion at all. The really cool part about this is beyond all of this, I even further then took this interstage duct I turned into a vortex tube, because the fluid coming in is going to be rotating, and as it decreases in radius, it's going to spin up, as this whole thing is already spinning too. But the fluid going through here will speed up in its rotation as it comes here, and you will get it. Again, this needs to be long enough. I did it short for the sake of being on the paper and clarity. But having this vortex tube means only the hot air will come out here, and the thermal energy can go towards some of the electrolysis. It won't be a lot, but it's some. But why this is the most important is that the colder air is then sucked through, or pushes its way through the slight vacuum, that the inner half of these discs works as a second vacuum pump. So like this is a really large one, but these inner discs allow it so that the fluid comes through here, and then this little short distance of the disc stack it won't be a lot, but it'll keep fluid going out. As the discs rotating, it draws it out, and then it comes out here. But out here then, the fluid being drawn through here will be cooled, which will further cool this side of the thermoelectric gradient so that you get an even higher potential output. This was my big, huge idea that I came up with years ago, and I'm literally just still trying to get these going, because once these are all finalized, I can start mass producing all of this. And I'm steps away from being able to get there. And now where this finalizes at, I had then further designed this so that this was just a solid cylinder, if you will, so that fluid coming in does the thermoelectric here, goes to the vortex tube, comes out to the electrolysis disc stack. You produce oxygen and hydrogen between the two disc sides. Obviously, there's going to be a bunch of little thin discs inside of each of the stack. I didn't draw them, so for clarity, again, over here, you'll have just as many of the discs here as you would in this side and this side. So what happens here is you get oxygen on this side, hydrogen on this side. The hydrogen is separated to here. The oxygen is separated to a pre-cooling chamber. And so basically, I turned that whole section here in between the two stages into the flame tube or combustion can that shrouds the center part here. So any heat produced in the combustion of this oxygen and hydrogen goes out to here, and I made it so that these are the Tesla valve rocket rotors, so that all of the combustion from this combustion can that goes actually down the length of the multi-stage rotor ends up burning and then providing reactionary force out. I just did this for clarity here, but you'll have an input of fluid in here that's coming out, and then all your excess goes out this way. So thermoelectric in cools this tip, creates a bigger gradient, produces more hydrogen and oxygen here. Those two are separated. They are then mixed and burnt down the length of this inner combustion can, and then go out radially and then tangentially around the rotor in the opposite direction, so that the fluid exiting the rotor provides torque in the drive direction with this. So this input will be pointing this way, but the exhaust of this rocket rotor will be pointing the opposite way. Stationary torque from throwing the fluid that way, torque in this direction, and then the fluid from spinning in the turbine gets torque in the same direction. So you get the reactionary that way and you get impulse this way all together. And now this could be further separated. You could slide these down. You make this as long as you want. Make this like a 4-foot tube if you wanted. Scale it up, whatever you need. You can see right here, this Tesla valve rocket rotor provides a reactionary torque in the direction of rotation with the Tesla turbine, which is impulse driving in the same direction.
Once that water turns into steam, it has no other option but to escape through the tiny nozzles placed in the arms, arranged tangentially to the center of rotation. These arms act as micro-rockets that propel the entire device around itself.
Yeah, this turbine is not a great way of producing power, but it's a great way of demonstrating how reaction turbines work. Tiny rockets propelling stuff around itself. I should probably put that on a t-shirt. You heard it here first. Don't forget to subscribe.
And where do you think he heard it from? Tesla valve rocket rotor. So you get thermoelectric, hydrolysis, and reactionary combustion can, flame tube mixing, and Tesla valve rocket rotor, and thermoelectric out exhausts through here. This could be steam and hydrogen all done in one. So you have steam input. The steam input and temperature gradient from the steam input will build up hydrogen and oxygen inside the rotor here and then burn it for more torque, which is, again, this is heat gradient from the rotor that wasn't getting used to begin with. So by utilizing that heat gradient, you're making use of some of that energy to produce some more fuel that wasn't going to get used. And also you're going to get the highest friction heating of the discs from the fluid at the tips. So that'll further add to the temperature gradient alone. Steam input only, and then when you burn the hydrogen and oxygen, well, you get more water, so it just makes more steam. All of that then goes to a vacuum condenser. Ta-da! Thermoelectric, hydrolysis, disc stack, combustion can, Tesla valve rocket rotor, steam, combustion, hydrogen turbine for both rotational mechanical energy output, and if you want, you can even siphon off some of the DC voltage potential across the whole rotor here.
So, this is Charlie, and what makes him special enough for me to make a video about him is the fact that he built this weird turbine.
If you check out Integs's recent video, I'll put it up right here, by doing his gyroids inside of his electrolysis or hydrolysis machine, and then by the end of his video, he decides to start using a bunch of thin discs because you get a ton of surface area. That was the whole point of this specifically. This was my grand idea that I came up with years ago, and I've been building to it, but haven't gotten there. And I'm sorry, Joel, but you made your video, and I'm like, okay, man, I gotta tell people. I'd already made a video about this years ago. It wasn't very well explained, but I needed it for the timestamp, and you can see it up here on my YouTube channel. No one will ever see it, but I posted it there so I could get a real timestamp of when I actually came up with this. Hope you guys enjoyed that.
This was a good idea, but it was short-lived. It works, but just for a while. It doesn't matter, because I just realized something. This is not the best way of getting the most surface area of a certain geometry. Just think about it.
If you have a cylinder, the best way of getting the most surface area in there is to stack a bunch of very thin discs on top of each other that are separated by a very small gap. Half is connected to positive, the other half is connected to negative, and ta-da! Perfect generator. My lattice is contained in a cylinder of 60 mm in diameter and 100 mm in height, and it has about 132 square inches of surface area. To get the same area with 60 mm discs, provided that I use 0.1 mm sheet steel, I would only need 15 discs to get the same area. Even if I use 2 mm spacing between them, that would only be 32 mm high. For the spacers, I could just use an outer ring with holes on the perimeter, but the steel discs are too thin and need support all over, and not just on the outer edge. Instead, I designed the 1.3 mm thick gyroid spacer. In this way, the disc has support all over, and because of the unique geometry of the gyroid, the gas doesn't get trapped. I am actually pretty proud about this design. The spacers I printed in my Form 4 in batches of 10. That was easy. The hard part was removing all the support material by hand. It took me an entire morning to do that. So this works like this.
Now where do you suppose you came up with that idea?
You heard it here first. Don't forget to subscribe.